Something happened on September 15th, 2017, that most of humanity simply watched, nodded at, and moved on from. A spacecraft fell into a planet. NASA called it a planned disposal. The news covered it for a day. Social media posted a few dramatic images, and then the world forgot. But here's the question nobody is asking. What if that moment wasn't an ending? What if it was the beginning of the most unsettling scientific unraveling in human history? Because right now, in 2025 and 2026, scientists digging through the archived data that Cassini transmitted before its death are finding things that are rewriting not just astronomy textbooks, but the fundamental assumptions we hold about life, about time, and about how alone we truly are in this universe. And the world is only now beginning to understand what Cassini actually saw. There was a machine built in the 1980s, funded across 3 decades, launched in 1997, and sent on a 7-year journey across nearly 2.2 billion miles of empty, freezing space. It carried no astronauts. It carried no passengers. It carried something far more valuable: 12 scientific instruments, a European lander named Huygens, and enough curiosity to outlast its own mission by 9 years. That machine was called Cassini, and what it saw when it arrived at Saturn in 2004 would take the scientific world another 20 years to fully comprehend. Think about what that means. 20 years, not 20 minutes of computation, not 20 months of analysis, 20 years of humanity slowly, painstakingly, incompletely processing what one spacecraft showed us about a planet that hangs in our own solar backyard. And we still are not done. The data Cassini sent home before it burned to nothing is still being opened, still being analyzed, still producing discoveries in 2025 that are making planetary scientists stop mid-sentence and recalibrate everything they thought they knew. This is not a story about a mission that ended. This is a story about a revelation that is still unfolding. But to understand where we are now, you need to understand what Cassini actually did. Not the sanitized version, not the press release version. You need to understand the full picture of what this spacecraft accomplished. Because only then does the weight of what scientists are finding today begin to land with the force it deserves. When Cassini arrived at Saturn, it entered a system that astronomers had studied from Earth for 400 years. Since Galileo first squinted through his telescope in 1610 and saw what he thought were ears on either side of Saturn, humans had been trying to decode this planet. Christian Huygens correctly identified the rings in 1655. Giovanni Cassini himself, the 17th century Italian-French astronomer the spacecraft was named after, discovered the gap in the rings that now bears his name. For centuries, Saturn was the ringed wonder of the solar system. Beautiful, distant, largely understood, or so we thought. What NASA's Cassini spacecraft found when it actually got there, orbiting Saturn for 13 consecutive years and making 294 complete orbits of the planet, was not the Saturn we thought we knew. It was something stranger, something more alive, something that broke almost every model scientists had constructed to explain it. And here's where it gets interesting, because the closer Cassini looked, the more questions it generated. Every answer produced a deeper puzzle. Every discovery opened a door that led to another locked room. Let us start with Saturn's rings, because that is where the story begins to get genuinely strange. For generations, astronomers assumed Saturn's rings were ancient, remnants from the formation of the solar system itself, roughly 4.5 billion years old. They were assumed to be primordial, frozen relics of the early universe. That assumption was so deeply embedded in scientific thinking that almost nobody questioned it. It was simply treated as settled fact. Then Cassini performed its grand finale, 22 daring orbital dives through the 200-mile gap between Saturn and its innermost ring, and the data that came back shattered that assumption completely. What Cassini found in those final dives was that Saturn's rings are young, astonishingly, almost impossibly young by cosmic standards. The measurements of ring mass, combined with the rate at which microscopic meteoroid dust darkens the rings over time, pointed to an age of no more than a few 100 million years, and possibly far less. Some calculations suggest the rings may be as young as 100 million years old. To put that in perspective, when Saturn's rings formed, dinosaurs were already walking on Earth. The rings are not ancient cosmic remnants. They are a recent event in solar system history, and the universe had already been running for over 13 billion years by the time they appeared. Read that again. The most recognizable feature of the most recognizable planet in our solar system might be younger than the dinosaurs. That is not a small correction to the scientific record. That is an earthquake in planetary science. And what caused them? The leading theory involves a catastrophic collision, perhaps a large moon or comet that strayed too close to Saturn and was torn apart by gravitational forces, its shattered remains spreading into the elegant ring system we see today. But here is what that implies, and this is what most science coverage fails to mention. If Saturn's rings are that young, then billions of other planets in our galaxy that have rings might also have formed them relatively recently. Rings are not permanent features. They are temporary. They are scars, and Saturn is currently wearing one. But that is not even the most important thing Cassini found. Not by a long distance. In 2005, during one of its early passes over Enceladus, a small, seemingly unremarkable moon of Saturn, barely 313 miles in diameter, covered in ice so bright it reflects almost all sunlight. Cassini detected something that made the mission science team stop cold. There were geysers, massive, active geysers erupting from the moon's southern pole, blasting columns of water vapor and ice particles hundreds of miles into space. A tiny frozen moon in the outer solar system was erupting with liquid water. And that water was not just water. When Cassini flew directly through those plumes, which it did multiple times, tasting them with its instruments like a spacecraft with a tongue, it found organic molecules, carbon-bearing compounds, the raw chemical alphabet of life. This was extraordinary enough on its own. But here is what nobody told you clearly enough at the time. Cassini's findings on Enceladus did not just suggest the moon might have water. They revealed that beneath that frozen shell, there's a global ocean, a worldwide liquid water ocean several miles deep, sitting atop a rocky seafloor being heated from below by hydrothermal vents, the exact same mechanism that powers life in the deepest, darkest trenches of Earth's oceans, where sunlight never reaches. In those Earth trenches, entire ecosystems thrive without a single photon of solar energy, just chemistry, heat, and water. And Enceladus has all three. This moon, smaller than Texas, quietly orbiting Saturn over 1 billion kilometers from the sun, is generating the conditions for life internally, right now, as you read this. And now, in 2025, scientists going back through Cassini's archived data are finding that it is even more significant than anyone realized. In October 2025, researchers published findings confirming that the organic molecules detected in Enceladus's plumes, the ones Cassini physically flew through, are not surface contaminants. They are not the result of radiation processing on the moon's icy exterior. They originated inside the ocean itself. They came from below. The molecules identified include aliphatic esters, alkenes, heterocyclic compounds, and nitrogen and oxygen-bearing organics, complex chemical structures that, on Earth, are not accidental background noise. They are the precursors to biochemistry. They are what you find before life or alongside it. Think about what that means. A spacecraft that burned up 8 years ago just provided the evidence, in 2025, that a moon of Saturn may have an ocean cooking organic chemistry in the dark beneath billions of tons of ice. The mission is over, the spacecraft is gone, but it is still making discoveries. And then, in November 2025, another paper landed. This one from researchers at Oxford University, the Southwest Research Institute, and the Planetary Science Institute. What they found using Cassini's infrared spectrometer data was something that overturned a key assumption about Enceladus. It was believed that the moon's geological heat was concentrated primarily at its south pole, where the famous tiger stripe fractures and geysers are located. Scientists assumed the North Pole was cold and inactive. They were wrong. The new analysis confirmed heat flow at Enceladus's North Pole as well, approximately 7 degrees Kelvin warmer than models predicted. Both poles are losing heat. The entire moon is warm. This means Enceladus is generating far more internal energy than previously calculated. And more importantly, it means the ocean beneath is not a temporary, local anomaly. It is stable. It is global. It has been stable across long geological time periods, long enough potentially for life not just to begin, but to evolve. The lead researcher put it plainly. The data highlights the need for long-term missions to ocean worlds and admits that the data does not reveal all its secrets until decades after it has been obtained. Read between those lines. A scientist is telling you that a spacecraft we sent to Saturn, which finished transmitting in 2017, is still surprising us in 2025. And if it is still surprising us now, what does the next decade of analysis hold? But this is where the story escalates into something even more difficult to sit with. Because Enceladus is not the only world in the Saturn system that Cassini pointed us toward. There is Titan. Titan is Saturn's largest moon, and it is in a category entirely its own. It is the only moon in the solar system with a thick atmosphere. Not a thin wisp of gas clinging to a rock, a genuine, dense, nitrogen-rich atmosphere with a surface pressure 1.5 times that of Earth at sea level. When the Huygens probe, carried by Cassini, descended through Titan's atmosphere on January 14, 2005, and landed on its surface, it became the most distant landing in human space exploration history. What it found was not a barren wasteland. It found a world with weather, with rain, with rivers, lakes, and seas, not water, but liquid methane and ethane, hydrocarbons that on Earth are gases, but in Titan's minus 179 degrees Celsius, surface temperatures behave exactly like water does here. They pool, they flow. They carve channels into the landscape. They evaporate and return as rain. Titan has a methane cycle the way Earth has a water cycle. It is a world running a version of Earth's chemistry using entirely different ingredients, and underneath its icy crust, evidence gathered by Cassini suggests there may also be a liquid water ocean, much deeper than Enceladus's, but present nonetheless. Scientists studying the way Titan flexes under Saturn's gravitational pull, a measurable wobble in its orbit, concluded that this flexing is too large to be explained by a solid interior. Something liquid is sloshing inside. Titan is not just a cold, orange alien world. It is potentially a two-layer ocean world with an exotic chemistry surface and a water-ocean interior. It is a place where life might have found not one, but two completely different environments to explore. What most people are not seeing is the full implication of this. Within a single planetary system, Saturn's system, Cassini found evidence for not one, not two, but at least two moons with subsurface liquid oceans, one with confirmed organic chemistry of oceanic origin, and one with an entire exotic liquid-based surface chemistry. The lesson is not just about Saturn. The lesson is about the universe. If one solar system contains this much liquid chemistry, this many potential biological environments, then what does that say about the billion other planetary systems in our galaxy? The math becomes staggering. The implications become almost impossible to contain within the normal vocabulary of science. And this is where everything changes, because the question is no longer whether life could exist elsewhere. The question is why we assumed it couldn't. Now let us talk about what Cassini did in its final hours, because this is the part that tends to get lost in the drama of the spacecraft's death. On September 13, 2017, 2 days before its final plunge, Cassini used its wide-angle camera to capture 42 red, green, and blue images of Saturn and its rings. Scientists stitched these together into a final mosaic, a farewell portrait of the planet the spacecraft had orbited for 13 years. The scene included 6 of Saturn's moons: Prometheus, Pandora, Janus, Epimetheus, Mimas, and Enceladus. It was, in the truest sense, a goodbye. A machine saying farewell to a world it had come to know better than any human ever would. Then, hours later, Cassini turned its antenna towards Saturn. Not toward Earth, toward Saturn. Because in those final moments, it was not transmitting pictures. It was sending back real-time scientific data from inside Saturn's atmosphere, measurements of atmospheric composition, magnetic field readings, particle densities, information no spacecraft had ever collected from that position before. Cassini was giving everything it had until the moment atmospheric drag overwhelmed its thrusters and it began to tumble. The signal died at 7:55 a.m. Eastern Time on September 15, 2017. The team in the control room at JPL sat in silence. Some wept, because they understood what had just ended and what might never be repeated. The Cassini-Huygens mission cost approximately $3.26 billion over its lifetime, roughly the cost of one large professional sports stadium when you place it in that context. For $3.26 billion, humanity received over 450,000 images, 635 gigabytes of scientific data, 3,948 scientific papers, and a profound, irreversible shift in how we understand the solar system. That is what a fully functioning, long-duration deep space mission produces. Not a headline, not a news cycle. An entire paradigm shift delivered quietly in terabytes across 83 light minutes of empty space. But the financial argument only matters if you understand what that data is still doing. Because the data did not stop working when Cassini stopped transmitting. Scientists at Oxford, at the Southwest Research Institute, at Caltech's Jet Propulsion Laboratory, at universities across Europe and the United States are still mining it. The October 2025 findings on Enceladus's organic molecules were not new data. They were new analysis of old data, using better tools, sharper algorithms, and more powerful computing than existed in 2017. And the findings from November 2025 about Enceladus's North Pole heat flow were built from Cassini's composite infrared spectrometer readings, an instrument that was producing data for 13 years. Scientists needed decades to extract the signal from the noise. They needed supercomputers running simulations to separate the subtle temperature variations caused by genuine heat flow from the daily and seasonal surface temperature swings of a frozen moon nearly a billion miles from the sun. The lead researcher on that North Pole study said something that deserves to be heard clearly. She said, "Our study highlights the need for long-term missions to ocean worlds that may harbor life, and the fact that data might not reveal all its secrets until decades after it has been obtained." That is a scientist in measured academic language telling you that our most powerful space missions are time capsules, that we send machines to distant worlds and then spend generations learning what they found. Cassini has been silent for 8 years, and it is still teaching us things we did not know existed. Here is what that means for the future. In 2024, the European Space Agency formally announced that Enceladus was one of its top targets for a future mission. Preliminary studies have already begun. The planned spacecraft not yet funded to full development, but already being designed in concept, would travel to Saturn, enter orbit, and make direct contact with Enceladus's surface and plumes. It would collect samples that Cassini could only taste from a distance. It would carry instruments that could definitively test for biosignatures, chemical signs of life, in the material erupting from that moon's hidden ocean. For the first time in history, we are not just speculating about whether a particular world could support life. We are building a machine to go and check directly. And simultaneously, NASA's Dragonfly mission, already funded, already in development, scheduled for launch in 2028, is heading to Titan. Dragonfly is a rotorcraft lander, essentially a nuclear-powered drone the size of a large SUV that will fly through Titan's thick atmosphere and land at multiple locations on the surface, sampling the chemistry of this methane-soaked alien world. The science cases for both Dragonfly and an Enceladus mission were built directly from what Cassini showed us. Without Cassini, neither mission would exist. The data Cassini sent home is not just sitting in archives being analyzed by academics. It is actively guiding where humanity sends its next wave of exploration. Cassini did not end the mission. Cassini opened the map. But let us pull back for a moment, because there is a dimension to this story that almost never gets discussed, and it is perhaps the most profound of all. Every time a new Cassini-derived discovery lands in a journal, whether it is about organic molecules in Enceladus's plumes, or heat flow at its North Pole, or the young age of Saturn's rings, there is an implicit question underneath the finding that nobody in the official press releases ever quite says out loud. And that question is this: if the conditions for life exist in multiple places within our own solar system, conditions we only discovered because we looked closely enough, then what were we assuming all these centuries when we looked at the stars and concluded we were probably alone? The assumption of solitude, the deep, quiet, culturally embedded belief that life is rare, that Earth is special, that the universe is mostly empty of biology, is not a scientific conclusion. It was a default assumption born from ignorance. We assumed life was rare because we had only looked at one place and found it. We assumed our chemistry was unique because we had never sampled another ocean. Cassini went and sampled another ocean. It flew through the spray of a moon's interior, tasted the molecules rising from a seafloor 1 billion kilometers away, and found the same alphabet the universe used to write life on Earth. The letters are the same, only the words are yet to be confirmed. What Cassini revealed is that the universe is not reluctant to create the conditions for biology. It does so generously, quietly, in ice-covered oceans, circling gas giants, in methane lakes on orange moons with nitrogen atmospheres, in hydrothermal vents, heating water that has never seen sunlight and never needed to. The conditions are not rare. The conditions appear to be common. What remains unknown, what remains the great suspended question of our time, is whether conditions translate into life. Whether chemistry, given enough time and energy and liquid, reliably produces biology, or whether there is one more barrier, one more threshold, that we have not yet identified or understood. That question is not answered. It may not be answered in our lifetimes. But here's what has changed because of Cassini. We now know exactly where to look. We know the address. We know Enceladus. We know Titan. We know the plumes and the seafloors and the tiger stripes and the methane seas. We are not searching blindly anymore. We are navigating with a map that a dead spacecraft drew for us 8 years ago and is still drawing today, in the hands of scientists pulling secrets from data that was collected by instruments no longer functioning, aboard a machine no longer existing, over a world no longer visited. There is something almost literary about that, something that resists easy summarization. A machine built by human beings, launched before most of today's college students were born, destroyed itself on purpose to protect the very moons whose oceans it had just helped reveal as potentially alive. And the information it gathered in its life is still expanding our understanding of the universe years after its death. Cassini chose its own ending so that Enceladus and Titan would remain uncontaminated, pristine, preserved for whoever comes next. The spacecraft was deliberately crashed into Saturn rather than risk it drifting into Enceladus or Titan and potentially contaminating those worlds with Earth microbes, because scientists took seriously the possibility that something might already be living there. Read that one more time. NASA destroyed a $3.26 billion spacecraft, partly to protect the possibility of alien life on Enceladus. That is not a footnote. That is a declaration of what the scientific community actually believes about that moon. And so we arrive at the present, at 2025 and 2026, at a moment when Cassini's data is producing new papers, new revelations, new recalibrations, almost every quarter. At a moment when the European Space Agency is designing a mission to the moon Cassini pointed us toward. At a moment when Dragonfly is being assembled to fly through skies that Huygens first photographed 20 years ago. At a moment when supercomputers are running models of Enceladus's interior using measurements taken by a spacecraft that no longer exists. At a moment when the north pole of a frozen moon, 886 million miles away, has just revealed that it is warmer than anyone expected, and that warmth means stability, and stability means time, and time means possibility. The question is no longer whether Cassini changed what we know. It did. The question is whether we are paying sufficient attention to what it is still telling us. Because in the noise of geopolitics, economic cycles, technological disruption, and the relentless velocity of daily modern life, the quiet papers being published in journals like Science Advances and Astronomy are delivering one of the most consequential stories in human history. They are building, piece by piece, revelation by revelation, the case that our solar system contains multiple worlds capable of hosting life. And if our solar system does, then the universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, many circled by icy moons with subsurface oceans, is almost certainly full of it. Cassini sent its last signal on a September morning in 2017. The team in Pasadena watched the light go out and knew they would never get another signal from that spacecraft. But what they did not know, what perhaps could not have been fully understood in that moment of grief, was that the light Cassini carried, the data it packed into 635 gigabytes of transmissions across a decade of exploration, would keep burning, would keep illuminating, would keep pushing back the darkness of our ignorance year by year, paper by paper, discovery by discovery. A spacecraft died so that science could live. And science, it turns out, is not finished with what that spacecraft saw. The next mission to Enceladus has not launched yet. Dragonfly has not reached Titan yet. The full archive of Cassini data has not been fully analyzed yet. The north pole of a moon, 806 million miles away, just told us something we did not expect. The organic molecules confirmed in October 2025 came from an ocean we have never directly visited. And somewhere in the terabytes, still waiting to be processed. In the measurements, still waiting to be cross-referenced, in the models still waiting to be run, there may be something else, something that changes the question entirely, something that does not just suggest life is possible elsewhere, but something that points a sharper finger in a more specific direction, with less margin for doubt than we have ever had before. We do not know what that is yet. We may not know for years, but Cassini left us the data, it earned us the time, and whatever comes next, whatever future mission reaches Enceladus, or Titan, and finally answers the question that one lonely spacecraft spent its life building toward, it will stand on the shoulders of a machine that fell into Saturn on a September morning, gave everything it had until the last possible second, and left humanity better equipped to understand its place in a universe that is far more alive, far more complex, and far more magnificent than we had the courage to imagine before we sent something there to look. The images have stopped, but the revelation has not.